Okay. Okay, so just a moment. Okay, so let me begin with the beginning of quantum mechanics, which was marked by the famous paper by Heisenberg. In this paper, he introduced the commutation rule that now brings his name. This commutation relation originally were related to representation of Lie algebras by several authors. In chronological order, I quote one of them, Weil, Majorana, Wigner, Mackey, Perelomov, and many, many others. However, these were generalization of Heisenberg commutation relations, replacing the Heisenberg commutation relation by a different Lie algebra. And they could not answer the basic question which has obsessed practitioners of quantum mechanics since its origin, namely, is there a purely classical framework from which these commutation relations arise? Okay, the goal of my talk today is to illustrate a very natural and conceptually simple answer to this question, showing how commutation relations which extend the Heisenberg one emerge naturally in classical probability. I hope that I have time to describe some of the perspectives that these solutions opens not only for mathematics, but for all disciplines where classical probability plays a role. That is physics, statistics, economics, sociology, biology, etc. So somebody may ask, if the answer to this question is so natural and conceptually simple, why it took more than almost 1 century to discover it? And the point is that, as you will see, the solution comes from the combination of 4 lines of research independently, with rare and tangential interactions, most of the time limited to very narrow technical aspects. And these 4 lines of research are quantum mechanics, the theory of orthogonal polynomial, classical probability, quantum probability. Once the single pieces of this discipline to be put together have been individuated, as you will see, everything comes down very smoothly. But what required time was to individuate the relevant pieces and to discover the right perspective to look at them. My talk will consist in 3 parts. The first part is devoted to show how every classical random variable naturally produces a quantum probability space. The main point is that the term naturally, that is, nothing is put by hands, as in other generalization or non-commutative generalization of other parts of mathematics, but everything is deduced from the combination of classical probability and the theory of orthogonal polynomial. The second part of my talk is devoted to show that every Jacobi equivalence class of probability measures on R is canonically associated to an extension of usual quantum mechanics. Canonically is again the crucial word. There is no artificial constructions. Then I show how quantum probability is covered, usual quantum theory is covered exactly by the Gaussian-Poisson class of measures for an equivalence relation that I will introduce. Finally, I will show how, in addition to commutation relation, the whole structure of quantum theory is naturally extended by this new approach. Finally, to show how what is the feedback of this new method to classical probability, showing that the new method allows to solve old open problem of classical probability and to make a natural bridge between classical probability, the theory of operator algebras, Lie algebra, Jordan algebra, and in all these cases, with classical probability, we will produce new constructive examples of these structures that deserve to be studied independently. So our starting point is the simplest, a single real-valued random variable with all moments. In this talk, the assumption of existence of real moments is essential, contrarily to what happened in my first talk, when this assumption was introduced only to make the exposition more intuitive. So let X be a random variable and denote mu, its probability distribution. So this is given by the standard formula for expectation value. As in my first talk, I will use always the same symbol for a probability measure on R, mu, and for the associated integral. So from now on, measure will mean for me measure with all moments, and random variable will be random variable with all moments. Recall that up to stochastic equivalent to give a random variable is equivalent to give its probability distribution, and therefore I speak indifferently of random variable and or of its probability distribution. So the algebra of complex polynomials in the classical random variable x will be denoted P of x. So this is the algebra of all complex combination of monomials. P is a commutative algebra, a star algebra, in fact, with the operation of pointwise addition, multiplication, and complex conjugation. And x to the power 0 gives the constant function 1. And we use the notation 1 as an identity of the algebra P, and phi 0 as a vector. Phi 0 will be called the vacuum vector for reasons that will be clear later. Now, P acts on itself by multiplication, and we, instead of using a separate notation for left or right multiplication, I simply use Q belongs to P to mean that Q is an operator, and Q times applied to the vacuum to mean that Q is a vector. Now, there is an important correspondence between measures on R and states on the polynomial algebra, because remember that a state is a normalized positive linear function. So a probability measure on the polynomial algebra gives a state phi by the definition that the phi expectation of P is the integral of P with respect to the mu measure. There is a partial converse to this statement, that is, given a state on P, then there exists a measure mu, which is usually not unique, measure mu on R, and this is the famous Hamburger moment theorem. Now, two random variables are called moment equivalent if they have the same moments, okay? But if they have the same moment, this means that they define the same state on the polynomial algebra. So the study of the properties of classical real-valued random variable X with all moments up to moment equivalent is equivalent to the study of the pairs P phi, such that P is the polynomial algebra and phi is a state on this polynomial algebra, okay? Now, remember that we defined in my previous talk an algebraic probability space as a pair is a state on A, and if is commutative, quantum otherwise, if it is not commutative. Now, every state on the polynomial algebra uniquely defines a scalar product on the polynomial algebra by means of the formula that you see, this formula 4. The semi-scalar product A times B is the expectation value of A star times B. Now, it is important to notice that X is an Hermitian operator on this, as a multiplication operator on this algebra. That is, it satisfies the following identity that you see. The important point is that there is a converse, that all the scalar product, that if a semi-scalar product is such that the multiplication by x is an Hermitian operator, then automatically this scalar product is induced by a probability measure. And the formula is given by this expectation value by phi0. Phi0 is the constant function equal to 1, I recall. So in the following, I have already introduced this notation. The left-hand side is when it is the identity of the 1 is the identity of the polynomial algebra. The right-hand side is when it is a vector. Now, the monomials are well known. Monomials are just the n power of the random variable. And by the principle of identity of polynomial, the monomials are a linear basis of P considered as a vector space. Then we introduce the degree filtration. The degree filtration is the set of all the direct sum of essentially is the linear span of the monomials of degree less or equal than n. And the dot over the sum means that the sum is direct, as we said before, by the principle of identity of polynomial. So P with n bracket is a degree less or equal than m. This family is an increasing filtration, and the union gives, of course, the algebra of all polynomials, because any polynomial is a finite degree. Now, recall the scalar, that we have a semi-scalar product. And then one can prove that one can define a notion of projection for semi-scalar products, and Pn will be the projection from all the polynomials to the polynomials of degree less or equal than m. Recall that a monic polynomial is a polynomial whose highest degree term has coefficient 1. Now, if you orthogonalize the sequence of monomials, you obtain a sequence of polynomial, and phi n is a monic polynomial of degree n. Moreover, phi n has real coefficients, and the family phi n by construction is an orthogonal linear basis of p phi 0. That is, remember, p considered, this symbol means p considered as a vector space, not as an algebra. Then we denote Pn, the multiples of the nth orthogonal polynomial, which means the orthogonal complement of the polynomials of degree less than n in the polynomials of degree less than n plus 1. And so we obtain what is called the orthogonal gradation. So the degree filtration as a space is obtained as a direct sum of one-dimensional subspaces corresponding to the orthogonal polynomial, and the same is true for the whole polynomial algebra. Okay, so, and this sum are orthogonal and direct. When you have a semi-scalar product, orthogonal does not mean it implies automatically direct. Now, we have the most important result, which is the old result 150 years ago. This is called the Jacobi theorem. The Jacobi theorem says the following: if you multiply the nth orthogonal polynomial by x, then you obtain something which is orthogonal to all other orthogonal polynomials, with the exception of 3, namely n when k is equal n minus 1, n or n plus 1. Moreover, there exist two sequences, alpha n and omega n, of real numbers, such that x phi n satisfies this famous three-diagonal Jacobi relation. Moreover, the alpha n is obtained as expectation value of x, and since x is Hermitian, you see that alpha n must be real, and from and then you obtain the following recurrence relations on the omega n. Then omega n is strictly greater than 0 whenever the norm of phi n minus 1 is different from 0. And conversely, if the norm is 0, then the norm of any other phi m for m greater or equal than n minus 1 will be 0. This implies that we can always choose the omega n with the following fundamental property. If some omega n is 0, then all omega k with k greater or equal than n will be 0. And the equation 14 will be called the Jacobi three-diagonal relation. In a moment, I will project again this equation. But a sequence that satisfies the property that we just deduced from the Jacobi theorem will be called the principal Jacobi sequence. Now, the main structure theorem in the theory of a one-dimensional orthogonal polynomial is Favart lemma, which is the converse of Jacobi theorem. Jacobi theorem says that to every polynomial we associate two sequences with the properties that we said before, and the Favart lemma said the converse, that given these two sequences, we can always associate a unique state on the algebra of polynomials of the random variable x with distribution mu, which satisfied the Jacobi induction relation with respect to these sequences alpha n and omega n. Now, from now on, we suppose that the norm of all the phi n are different from 0. This is not necessary, but simplifies the discussion. And if we introduce this option, we are simply neglecting measures with support in a finite number of points. Then now we have the gradation. The gradation is the orthogonal gradation, and phi n is the monic orthogonal polynomial. Now, look at the Jacobi relation. This is a relation on that relates phi n multiplied by x with phi n plus 1, phi n and phi n minus 1. So, since these phi n are mutually orthogonal, it is natural to introduce three different operators. You see, phi n, which maps that maps phi n into phi n plus 1, and we call creator. Another operator that maps phi n into alpha n phi n, and we call preservator. And the third operator, a minus or a simply, that maps phi n into omega n phi n minus 1, and we call annihilator. Since the phi n are mutually orthogonal and with the norm different from 0, they are linearly independent, so there are this operator a daga, a0, a are uniquely defined. And therefore, this vector identity, which was the original Jacobi identity, can be interpreted as a single operator identity. This is for every n, and this is a single operator identity. Now, one also proves that the adjoint of a daga is a minus. We will also write a, and that a minus applied to the vacuum is 0, and this justifies the names. That is, the vacuum is annihilated by the annihilator. That is why this is called the annihilator. Now, the operator identity, the fundamental operator identity that we just proved, is called the quantum decomposition of the random variable x. And the operator a plus, a minus, a0 are called the cap operators for creation, annihilation, preservation. Now, you see, for 150 years, the Jacobi relation has been studied by analysts. And if in quantum probability, we look at the same relation, but from an operator point of view, as an identity of operator, and in probabilistic terms, this means that the classical random variable is a microscopic structure defined by the operators a daga, a minus, a daga, creation, annihilation, and preservation. Okay, so this new point of view has a lot of deep implication. Let us see some of them. First of all, we will associate to a classical real-valued random variable x a quantum polynomial algebra. And this association is canonical because the quantum decomposition of x is canonical. So remember quantum probability, that the algebraic probability space is a pair of a star algebra and phi. Now, when we have our variable, random variable x with all moments, we have the natural classical probability space of the polynomial algebra of x and the expectation given by the distribution of x. But now we have a quantum decomposition. So we can consider a larger algebra, not the algebra generated by polynomial in x, but the algebra generated separately by polynomial in the non-commuting random variable a daga, a0, and a. So we will denote phi, a daga, a0, a minus, a0 to be the algebraic linear span. That is the star algebra generated with identity generated by these three operators. This is automatically a star algebra. And since we have the vacuum vector, which is defined and in the domain of all these operators, which usually will be unbounded, all the operators in this polynomial algebra, we can define a state in this larger algebra by this formula. We define the vacuum state on the larger algebra for any polynomial in the non-commuting variables, a daga, a0, as the expectation value with respect to the vacuum state. Now one can prove that the restriction, in fact, by construction, the restriction of the vacuum state to the classical algebra of polynomial algebra is exactly the state from which we started. So in the future, we will identify the two states. So summary, an analysis of the classical algebraic probability space naturally produces the quantum probabilities, a quantum probability state which includes the starting one, and with the property that phi vacuum restricted to phi is equal to the polynomial algebra is equal to phi, the original distribution of x. So in the following, we will identify the two states. So the conclusion of the first part of my talk is that non-commutativity arises in probability, classical probability, not artificially, but naturally deduced from this 150-year-old result, which is Jacobi theorem. So this solved the first of the mystery that I listed in my introduction, that is, from where non-commutativity arises in quantum theory. The answer is from classical probability combined with the theory of orthogonal polynomial. But this is only the first step. In fact, we have seen that the generic non-commutativity is not sufficient because we want to understand Heisenberg commutation relation. And this is the next step of the investigation. So now we show that every random variable is canonically associated to some commutation relation. Let us see why. Because remember the definition of creator and the definition of annihilator. So if I apply first a creator and then an annihilator, I obtain the omega n plus 1 times phi n. But if I apply first annihilator and then creator, then I have omega n times phi n. Therefore, this gives automatically the commutation relation on the basis, on the orthogonal basis. But since this is an orthogonal basis, the scalar combination relation can be written as an operator commutation relation. But for this, we need to introduce the number operator. The number operator is the operator which applied to the nth and multiplied on a polynomial. So this will be true for all functions of lambda. If f is any function from the natural integers to c, the function f lambda applied to phi n is fn times phi n. Therefore, the vector commutation relations are equivalent to the operator commutation relation, where this delta simply means the first difference operator, first order difference operator, which is omega lambda plus 1 minus omega lambda. Remember that omega lambda is given a meaning by this identity, which is true for any function defined on the natural integers, and the lambda the spectrum of lambda is in the natural integers. Okay, so we have this commutation relation. So if we want to solve our second problem, we must answer the following questions. Are the Heisenberg commutation relation included in this formula 30 that is written here? And if they are included, to which kind of random variables they are associated? And the answer is obtained by noting that the simplest possible commutation relation is when this operator is in fact a multiple of the identity operator, the multiple of the identity operator. So now let us go to the deduction of Heisenberg equation. Now, in order to deduce Heisenberg equation, we need a result from this new approach to orthogonal polynomials. Namely, remember that a measure is symmetric if for every Borel set the measure of I is equal to the measure of minus I. And this implies that the odd moments vanish. The converse is not true, but only up to moment. Okay, we take the weaker definition. So a classical random variable is moment symmetric, so all odd moments vanish if and only if in the quantum decomposition the A0 term, which is the symmetric term, is equal to 0. Okay, if you remember my first talk, you see that typically A0, when we go to processes, is responsible for jumps. Okay, and then we have the main theorem that says that given a natural number, remember we wanted to solve the problem. Heisenberg equation gives the commutator of AA daga a multiple of the identity. And is this obtainable by the theory of orthogonal polynomial? The answer is yes. It is obtainable if and only if sigma is positive. So we have two cases. Sigma is 0, and in this case, we have the delta measure at 0. But if sigma is strictly positive, you prove that the Gaussian measure with 0 mean and variance sigma is the unique symmetric measures whose cap operator satisfy the Heisenberg equation. So Gaussianity is characterized by Heisenberg equation. And this will be true in any dimension, also infinity, but I cannot discuss multidimensional case. Okay, now the proof is very simple. It's simply based on the fact that the Jacobi coefficients of the Gaussian are multiple of the variance of the Gaussian. So since sigma is the variance, it must be positive. It must be positive. This is just the basic idea of the proof. I don't go into the details. Now let us introduce the equivalence relation between two Jacobi sequences, between two probability measures on R. We say that they are equivalent if the principal Jacobi sequence is the same. And the important point is that the Poisson measure is Jacobi equivalent to the Gaussian measure. And from the theorem before, this means that it has the same commutation relation. And in physics, the variance of the Gaussian, a special variance of the Gaussian, has a very important meaning, and it's called Planck constant. So we can, from classical probability, we can predict that the Planck constant is positive. Of course, we cannot predict the value of the Planck constant, which comes from physical arguments. So the Heisenberg and the Gauss, so we have proved that the Heisenberg commutation are commutation relation canonically associated to the Gauss-Poisson class, and the Gauss is unique symmetric measures. Okay, so it is not by chance probably that the intuitive attempts of Heisenberg led him to the discovery of the commutation relation canonically associated to the two most important and used classes of probability measures, which are in fact the Gauss and the Poisson measure. Okay, so in the previous section, we have seen that express the commutation relation in terms of creation and annihilation. But at the beginning of my talk, I gave the Heisenberg, the original Heisenberg relation, which is formulated in terms of momentum and position, which, remember, position is now generalized by the arbitrary random variable x with all moments. So our next problem is to deduce from classical probability the original formulation of Heisenberg commutation relation. And so we have to ask, how do momentum operator canonically arise in classical probability? The answer to this question is the following, that if you have a symmetric random variable, I give it as a definition. In fact, it comes out as a theorem from complexification but I have no time to discuss this. So I give it as a definition. The canonical conjugate moment to the classical random variable x is defined as in usual quantum mechanics to be I times a daga minus a. Remember that for symmetric random variable, you have at x is equal a daga plus a. Okay, so all symmetric random variable have a canonical quantum moment. So when this definition, as I already mentioned, when x is the standard Gaussian random variable, is reduced to the standard definition used in quantum mechanics. Okay. Now let us see what happens in the more general classical random variable. For more general classical random variable, you have that the commutator of position and momentum, you easily compute it in terms of a and a daga, and it is equal to 2I times the finite difference operator, omega lambda plus 1 minus omega lambda. But we know that in the Gaussian case with standard Gaussian case with unit variance, this d lambda is equal to 1. And so this commutation relation is exactly Heisenberg commutation relation. Well, up to a multiple 2. This is because usually in quantum mechanics, they define the position and momentum by dividing this by square root of 2 and also this by square root of 2. Okay. Now I will want to say an important problem, which is not a mathematical problem, but is a conceptual problem, but it's very important. Now we have proved that all symmetric classical random variable x have a canonically conjugated moment in classical probability. And so how to interpret? In the case of Gaussian random variable, we know the interpretation as momentum. But how to interpret the canonical momentum in terms of classical probability? This I think in many years, but it's not clear. We have to see case by case. We have to study special examples. So the consideration, so we have a translation code. Essentially, I will not go because I have not so much time. Essentially, orthogonal polynomial are in the translation code from classical to quantum. Orthogonal polynomial become n particle, so-called n particle vectors in quantum mechanics, and the orthogonal polynomial gradation becomes the n particle gradation, and the Hilbert, the pre-Hilbert space. In our case, we are using pre-Hilbert because omega n is strictly greater than 0. The pre-Hilbert space is what is called the boson-Fock space over the complex numbers. And you know, from complex to any Hilbert space, the transition is just functorial. It's easy to do. Now, third part of my talk, I want to go, what is the feedback for classical probability of this new approach? And the feedback, there are many, but I have no time, so I will concentrate only on what I consider the most interesting, one of the most interesting results, namely the Lie algebra classification of probability measures. Remember that any classical random variable is such that its creation and annihilation operator satisfy the following operator commutation relation. Okay, so this generates a Lie algebra. there is a smallest Lie algebra containing a daga, and 1. And this algebra is canonically associated. Of course, since it's a Lie algebra, it must contain the commutator, so it must contain d omega lambda. So it is very important. The structure of this Lie algebra strongly depends on the structure of the principal Jacobi sequence of the random variable. So but you know that in the Gaussian case, this Lie algebra is three-dimensional, that is closed. So it is very natural the following question. Are there other classes, in addition to the Gaussian, of real-valued classical random variables such that the star Lie algebra generated by A and A daga is finite dimensional? Remember, Heisenberg algebra is three-dimensional. Then we begin with the necessary condition. We have the following theorem. If all the omega n are strictly greater than 0, a necessary condition for the Lie algebra generated by A and A daga, L0x, to be finite dimensional is that there exist two numbers, n and capital K, such that the principal Jacobi sequence satisfies this difference equation of order n for any m starting from K. And remember that the delta operator is the difference operator omega n plus 1 minus omega n. This condition is necessary, but the condition is not sufficient. Why? Because if the Jacobi sequence satisfies this equation with n greater or equal than 3, nevertheless, the algebra L is always infinite dimensional. So there are only three possibilities for n to be well, three. There is, you see, okay, you will see later that also 0 can be concluded. Okay, I will come later to these three possibilities. Okay, so what does it mean, this condition? Since it satisfies a difference equation of order n, this condition simply means that omega n is a polynomial in n of degree less or equal than n, because this is a standard results in the theory of finite difference equation. So intuitively, we can say that the class of probability measures whose principal Jacobi sequence satisfies this difference equation for some n is the simplest possible class of probability measure, because at least satisfies the necessary condition for finite dimensionality. We know this is not sufficient, but at least is a condition. So it restricts the class of possibilities. Okay. So let us make quantitative this assertion. So to make quantitative this assertion, we introduce the notion of information complexity index, so a classical probability measure on R. So suppose that this necessary condition for finite dimensionality of the Lie algebra is satisfied. Then the map, we have already said, satisfies a difference equation of order n, but this equation is not satisfied everywhere for every m, but only starting from n greater or equal than k plus 1. Okay, so we call this pair of natural integers the information complexity index of the probability measure mu, which is the distribution law of x. Now let us consider the formal definition. So the formal definition of index is the this pair, small k and capital K, and small k is the minimum degree where the difference equation is satisfied, if such a minimum degree exists, but satisfied only starting from n greater or equal than 1. And we put the index of complexity to be infinity if there are no such pairs. Many other index of complexities can be introduced, but this is already gives a lot of information. Now take the simplest possibility class, 0. The 0 class, according to the definition, means 0K class means that the principal Jacobi sequence satisfies a first order difference equation. But first order difference equation means that omega n is constant. And therefore we have only two possibilities. Either the constant is 0 or not. The case 0 is just includes all measures supported in K plus 1 point, atomic measures. The case omega greater than 0 is much more interesting, because this class is called, not by chance, extended semicircle arc sign class, for the reason described below. So the class 0, 0, so the simplest, lowest level of complexity, corresponds exactly to the semicircle laws with the variance given by omega. I put here with the standard variance. Okay. The density for case omega is equal to 1 is this one. And you know that the semicircle law is the Gaussian for the free independence. Now, let us go to the next step in the hierarchy of complexity index. Next step is 0, 1. 0, 1 is the class of arc sign distribution. And this is the Gaussian for monotone independence. Okay. Now the third level of complexity is 0, 2. And this is not special name in quantum probability, but nevertheless it appeared in some central limit theorems in the sense of in some theorems of Conno. And this is probability density given by this formula, where C is a certain parameters. Okay. Now, when K is equal to 0, we call extended arc sign semicircle class. Okay. Now we come to the more interesting case, but we already seen 1/2 of this case. The class, the 1K, the class 1 means that it satisfies a second order differential equation. So it means that it's a polynomial of first order. Well, if we take K greater than 0, we know nothing. We unfortunately, classical probability don't know. I've never found which are the probability measure with this Jacobi sequence. Even the symmetric ones are not known. But if we take the simplest simplest element in this class, which means K equals 0, then you recognize that we have the Gaussian Poisson class. And we already know that the associated Lie algebra is the Heisenberg Lie algebra, which is 3-dimensional. The next step in complexity is the case in which we are level 2 of the degree. So the difference equation is 2 + 1, which is 3, and K is arbitrary, natural number. So the third order difference equation means that this is a polynomial of the omega n are polynomial of second order in n. And we know for K, again, with K equal 0, we know strictly greater than 0, we know nothing. But for K equal to 0, we have the class 2, 0, which means omega n is a second order degree polynomial in n for every n greater or equal than 1. Then this means it's a very famous class, which are the so-called non-standard Meissner distribution. Non-standard means because Gaussian and Poisson are Meissner, but they are called standard Meissner. Non-standard, there are 3 classes, but I will not come into the description of this. And the interesting result is this. If a classical probability measure, an index to 0, then the Lie algebra generated by its associated creators and annihilators is a central extension of SL2R. So you see that the SL2R is the algebra which comes 1 degree of complexity, characterizes the measure, the probability measures, which are 1 degree of complexity more than usual quantum mechanics. Okay, so this is a characterization, Lie algebraic characterization of Meissner measure. This was not known in the literature. The quantum probabilistic quantum probabilistic characterization, but we should say classical, because we have deduced it from classical probability. Okay, so the class, but this is an important concept. This means that the class of Meissner measures is as canonical as the Gaussian measures, but a step higher in the classification of complexity classification produced by the index of information complexity. I have no time to describe. This class was discovered before, well, was well known in probability, but the quantum meaning of this class was discovered before this new approach to classical probability in terms of orthogonal polynomial, and it is very strictly related with the quadratic quantization program. There are many, many papers on this, but my time is finished, and I want to leave open the possibility for a few questions, if there are. Thank you very much for your attention.
Dear Luigi, thank you very much for your talk. Dear colleagues, please, we wait your comments and questions.
I would like to say something.
Yeah, Albert Nikolaevich, please.
Luigi, text is prepared extremely well. And I think that if you will write the paper for our journal, Theory of Probability, it would be very good. Because I think that many probabilists don't familiar with the terminology of the quantum theory of probability. And so, tell me, is it possible to receive the paper for our journal Theory of Probability from you?
Sure, I will do with pleasure, because I am convinced that with this approach, there will be no longer a difference between classical and quantum probability. There will be only probability. The same happened with geometry. Nowadays, nobody distinguishes non-commutative, Euclidean and non-Euclidean geometry. One simply speaks of geometry. And in the following, this will be the same for probability. Nobody will distinguish commutative and non-commutative probability, and everybody will speak of simply of probability, as it should be.
No, and so, Luigi, we will be very happy if you will present the paper in this year or the next year. Next year, you know, I wrote you that next year is very interesting for us, because it's the jubilee of the Kolmogorov.
So this will be a fantastic occasion.
Yes,
yes. This will be really a fantastic occasion.
In our probability journal, practically no papers about the quantum probability theory. So please write.
I will do absolutely with the great.
And I think that we shall discuss with you by emails.
Yes. I will surely say, and some details, like, for example, number of pages and so on. This will be discussed. We will discuss by email. I'm not able to obtain the larger screen, but it doesn't matter. Okay. Thank you for the invitation.
One more question now. I want to ask you, is something published already about
Marek,
this?
one moment, wait, please. Yeah, Professor Malyshev, please.
Yes. One question only. Is already something published about this or not yet?
Well, there are a lot of papers which are published, a huge quantity of papers. but on this last topic is relatively recent, and so there is no survey. So maybe the one that I'm going to write for theory of probability will be the first survey entirely dedicated to the fact that quantum mechanics is, in fact, in the future, quantum mechanics should be taught as a branch of classical probability. This is the thesis that I have tried to convince you, because it is true, you have seen. Quantum mechanics is simply the Gaussian level of classical probability. And we have to investigate the upper levels. And the natural candidate is Meissner, because it is the unique class of measures in classical probability, which has a canonically associated finite dimensional Lie algebra. And moreover, this Lie algebra is one of the most famous Lie algebra of mathematics, which is SL2R.
Okay, excuse me, one more question. Is a classical physics become more understandable, the relation of classical physics with quantum physics? Because I guess this is the main problem. Classical physics, quantum physics, because classical physics is not probability, is not random, it is absolutely deterministic.
Well, depends which physics you mean. Classical mechanics is the
classical, no.
But statistical mechanics is only the,
I answer you. Classical physics consists of two parts. It is Newton mechanics, and Maxwell Lorentz electrodynamics. Two things, but this is the main thing in classical mechanics is time, it is space, of course, and it is absolutely deterministic movement.
And the same is in
without any randomness.
Wait a moment. In statistical mechanics, the randomness is induced by the randomness of the initial state. The dynamics is deterministic.
Excuse me, statistical mechanics now exists mostly as an equilibrium mechanics.
And also no, there are, in fact, from the stochastic, let me tell you, this is interesting. From the stochastic limit of quantum theory, we have obtained deep results on non-equilibrium, a very special non-equilibrium. But there are also many results. In any case, the stochasticity and in classical mechanics enters with the imprecise knowledge of the initial state. But in quantum mechanics is intrinsic, because one of the equivalent formulations of the Heisenberg principle is that if you have two incompatible observables and you have a maximal information on one, that is, you know all the values, you measure the value exactly in one moment, then the other one you cannot measure exactly, but only probabilistically. So it is intrinsic in quantum mechanics, probability.
Yes, of course, but in classical physics, absolutely not. I guess I will send you my new journals if you did not see them. About okay, and
I will read with pleasure.
Okay, good. Okay, thank you.
Dear colleagues, please question or comments from Professor Bajejka, please.
Thank you very much, and thank you, Gigi, Accardi, for a nice talk. When we work, sometimes I would like to say that from my point of view, you say that Wigner law and Arcus sinus law are important, but we are in Russia, so we should say that this depends to Chebyshev, and the polynomial is exactly Chebyshev polynomial of first kind. This is orthogonal Arcus sinus law, and Chebyshev second time, which orthogonalize Wigner measure square root of 1 minus x squared. And other interpolation, what is your, you are not your classification. We did sometimes, this is called Kesten measure, when he discovered on random walk, Kesten, on let's say free group or trees or KD graph of free group. This is tree, homogeneous tree, and that is very famous, but also you can do continuously. So I am glad that you, of course, the arcus sinus appears also in monotone, but also appears in conditional free when we deal with Speicher also. So I would like to say that arcus sinus appears many, many times. And this is Chebyshev polynomial of first kind. So if you like, because you mentioned that everything is important Hermite. No. I think we should say that Chebyshev is more important. So this is my comments, and thank you. Also, you mentioned Kono random walk, yeah, quantum. But of course, this is a special case. Some says or generalization of Kesten work, famous.
No, they are different. There is a technical difference.
I say the
which is very important.
Polynomials appear and that arcus sinus law. I don't say that is the same, but it's in that spirit. Yeah. And Kesten was student of Ulam, and Ulam was student of Stefan Banach. So you see, this is, and you know what is the Ulam and what is Kesten. So I should say that in that talk, we should say that thank for that important mathematician. Thank you very much, Gigi.
Dear colleagues, in other comments, please, Professor Sonin, your questions.
No, I'm not really a specialist in this area, so I cannot really appreciate your talk, but it's still very impressive. I have very narrow questions. We know that in probability theory, in classical probability theory, the concept of independence plays very important role. I'm wondering how it is reflected in your quantum probability.
Oh, I can only answer you with the theorem, which in fact is a theorem we proved with Marek Bozeiko many years ago. Given any probability measure with all moments, there exists a notion of stochastic independence for which this probability measure is the Gaussian. That is the result of central limit theorem. And then later on, so the notion of stochastic, I mean, this is what we call in there is an idea that was first formulated by Romuald Lenczewski, and he says that what in quantum probability we call independence are in fact hidden or masked dependence. So the good way, I think this philosophy is correct. The good way to understand the notion of independence in quantum probability in terms of classical is to think of them as constraints that we put not as in classical probability, we hide all constraints of the variables in the correlations, so in the joint probabilities and the joint expectations. But in quantum probability, we have an additional degree of freedom. We can, and now we have the same degree of freedom in classical probability. That is, we can code some constraints among the random variable in algebraic terms. So they are not independent, but they will satisfy some notion of independence, okay? Algebraic notion of independence, which means this fact has been recently proved in a paper with Lu for fermions. And so you see, it shows what we proved is that like there are the Maxwell-Boltzmann and Fermi-Dirac statistics, we teach in elementary course of probabilities. And now from quantum probability, we have generalization of this very famous classical statistics that have been obtained exactly in this way. You put a constraint in algebraic language, and then you use an algebraic formulation of independence to deduce the the probability and therefore calculate entropy and so on.
Okay, thank you.
I'm sorry, Luigi, I didn't understand what you have told about your result with Professor Bajejka. Can you repeat this phrase? What was the
statement of the theorem? The statement of the theorem is, given any classical random variable with all moments, then there exists a notion of independence. This is the hidden part. The notion of independence. In our paper, we introduced the notion of independence by introducing a generalized convolution between classical probability measures. Okay, but then later on in another paper with Lu and Chris Male, we gave a constructive central limit theorem, not in terms of convolution. And then two students of Bojejko, which is Lukasz and Kristek and Wojakowski, they proved that the constructive central limit theorem that we had proved gives rise exactly to the quantum convolution that we introduced with Bojejko. So this closed the circle.
And the convergence to in this generalized central limit theorem, the limit distribution is Gaussian or not Gaussian?
No, of course not. In general, not. The limit distribution is the distribution which you have used. The notion, you understand, the notion of convolution is that we gave with Bojejko is used the Jacobi sequences of the two probability measures. So you see, when the Jacobi sequences are very nonlinear function of the probability distribution. So if you want to translate in analytic language, it may be difficult. That is why the subsequent constructive theorem was important, because it gives you a concrete representation. And this is based on another notion which is important, which is called interacting Fock space.
Thank you. Thank you very much.
Please, more comments or questions?
Lena, I would like to tell a couple of words. Can I do
Of course, of course.
Okay,
Professor
first,
Sayano.
okay. First, thank you very much to Professor Accardi for his efforts to prepare this extremely nice talk. Now, I have just a couple of comments. A few times, Professor Accardi, you mentioned that the random variables you consider, they have all moments finite.
Yes.
Then you refer to the classical hamburger moment problem or theorem, but that theorem is about the uniqueness. You didn't mention this as a property, the uniqueness in terms of the moments.
Well, as I know, the uniqueness is dealt in some sufficient condition.
Yes.
Very famous, which are given by Swedish mathematician. Now I don't remember the name, but it's so famous that everybody of you knows.
Okay.
But the uniqueness is non-trivial. The existence is non-trivial because, for example, this is an open problem for analysis and for classical probability. There is no hamburger theorem in dimension greater or equal than 2. So existence is non-trivial.
Okay, I agree. Still, there is a lot of information available. Now you consider the property symmetric and moment symmetric.
Yes.
So this as equivalent notions.
Not equivalent. We have a counterexample in a paper with Kuo and Stan, in which we construct a measure which is moment symmetric, but is not symmetric.
Okay, a little bit joking, I will suggest to buy this counterexample. And also in the Gaussian case, you mentioned everything is okay. And about the Gaussian distribution, we can see there is an excellent paper by Albert Shiryaev in number 4 for last year, the volume of Theory of Probability and Applications, a paper about Chebyshev and his contribution to probability theory. So, and also, by the way, once again, I will mention the journal Theory of Probability. You mentioned the class of Meixner distributions, standard and non-standard. There is another paper, I think maybe in number 1 for last year or maybe the year before, by 2 Australians, quite interesting paper about the characterization. Of course, it is a classical probability, characterization of any kind of Meixner distributions. So this is what I wanted to tell it. Thank you very much again.
Yes.
We will be waiting for your paper.
But you mean a Gaussian distribution in 1 dimension or in more?
One dimension.
Ah, okay. But then the first characterization was in fact given by Meixner itself. What I presented today is a new characterization, which is purely in terms of Lie algebra.
Yeah, that's correct. I learned about this for the very first time. So thank you again.
Thank you.
Thank you. So I think today it was a very useful discussion. Luigi, thank you very much for your talk once more. And now I would like to give an announce for the following talk. It will be, please pay attention, it will be on March, because 23 of February is a holiday, so we will have our next seminar on the 2nd of March. The next seminar will be, the talk will be by Professor Dragovtsev from Ukraine Academy of Science, and the name of his talk, Intermittency of Local Times and Geometry of Mass Distribution in Stochastic Flow. I repeat in Russian, это перемежаемость локальных времен и геометрия распределения масс в стохастическом потоке. So, hope to see you at the beginning of March. And today we see a new participants of our seminar. If they would like to be in our list of seminar participants, please write to me or the secretary or to Vladimir Kutsenko, who is the secretary of our seminar. So see you at the beginning of
Excuse
March.
me, I want to say one word. So we will see in March if there will not be war.
In March, it's a working day, 2nd of March.
Okay. Thank you very much.
So today we finished our seminar. Goodbye to everyone.
Thank you.